In this example, we have a car that's driving on a straight, flat road. The acceleration of the car is shown in the acceleration time graph. The car starts from rest, reaches a maximum velocity of 45 meters per second, and drives at that for 5 seconds. The driver then applies the brakes, slowing the car to an eventual stop. At what time does the car stop? All right, so we know the car starts at rest and ends at rest. It hits a maximum velocity of 45 meters per second, and the time that it travels that velocity is 5 seconds. So you can see from the acceleration curve, right, the velocity starts from rest, it accelerates until it reaches a maximum velocity of 45, travels that for 5 seconds, then brakes until it comes to a stop. All right, so we want to get familiar with the problem, identify the regions of continuous motion. We'll find the acceleration as a function of time for each region, then integrate those equations to find the velocity as a function of time, and then use that velocity to find time. All right, so to get familiar with the problem, I always like figures. All right, so we have the acceleration graph. We're going to divide it into continuous regions, so A, B, and C. In each of those regions, the acceleration is continuous. All right, so we start from rest, hit a maximum velocity, then at point time t2, the velocity starts to decrease until it stops. All right, so we know that the initial time is 0. We know that the time between t1 and t2 is 5 seconds, and we don't know what time it takes for the car to stop. All right, so first we'll get the acceleration. We know the graph, and we know that this is just a line, so we write the equation of the line. The acceleration in part B is 0, and the acceleration in C is a constant -5. With the acceleration equations, we can integrate and get velocity. So we'll use a dv dt and rearrange it and integrate the acceleration. So we can do that for each region, right? And the initial limits for region A are 0, 0, right? Because it starts from 0, speed 0. We integrate it and we get a velocity equation for region A. In B, we don't need to do anything. We know that that's 45 meters per second. The problem gives us that. But this is also equal to the velocity of A at point time t1, right? So if we plug t1 into the equation for region A, we should get 45 meters per second. And then we integrate for C and get a velocity for C. But the initial limits, or the lower limits, are different, right? For the velocity, it's 45, because that's the speed that the car comes into region C with, and the time is t2. Now, on all these integrals, I always put just general variables at the top, so t and b, because if we have a general equation, it's much more useful. All right, so we have the velocity equations. We can draw a velocity graph. So this is how it looks in region A. It's constant in B, and because the slope of, the acceleration is -5, the slope of this one would be also -5. All right, now we can go on to the times. So before I said that the velocity in B is 45, but if you plug in t1 into the A equation, this will also be 45. So we can use this equation to solve for t1. And then we know t2 is just 5 seconds beyond that. We can use VC, the equation we got, to find out what the stop sign is, or the stop time is. So the BC at time stop is 0, of course. So we can plug that into the C equation and get a time stop of 23 seconds.